My name is Michal Šustr, and thank you all for coming, ladies and gentlemen. And tonight I will talk about a machine learning method that's called Generative Adversarial Networks. And I will shortly... Oh, a moment. Sorry. Yeah, okay. I will just shortly show you the contents of this lecture. So I will start with a motivational example. And then I will talk a bit about what is, how does these methods relate with unsupervised learning. And then I will talk about the GAN algorithm itself. Various methods that are used in GANs, training problems of them, and I will conclude with some final examples. So at first I'll show you the demo. And so generative adversarial networks are an interesting method that can generate examples of data. Basically, if you have images or other data distributions, you might be interested in generating samples from these distributions. So, for example, you would like to automatically generate things like faces or images of different sorts. And this demo that I will show you was trained on pairs of images where the input is some kind of an image and the output is image that has been transformed into a different style. So it could be thought of as a task of image translation, where as an input you get some kind of specification, and you would like to receive an output that has been modified with these methods. So, for example, there is in this example, the GAN has been trained on pictures of shoes, and if I modify the input shoe, I can draw something on it. For example, like this. It's actually a live demo, so it requests the server and paints the new picture. And if I would take some other random example, for example here, and draw something different, it will take the input and try to actually guess what was meant by this input. So it will fulfill the details into it. Some might be better, some might be worse. Or there's examples of cats. I'm not very good at drawing cats on a different display, but I can try. So if we add some other details, it will actually take it as an input and render additional details based on what we put in there. And I have actually some other examples here in the presentation. This is something my colleague made. So if you're interested in, I'll just, yeah. So if you have ever wondered what a Schrödinger cat looks like in a box, this is how it looks like. And there's other horrifying examples that you can find on the net. And so this is just a small demo to get you a little bit interested in what we might accomplish with these techniques. I'll show many more examples later on. but I would like to start with a bit of theory and then put in some examples to not make you asleep and then go on. So at first, I would like to ask you who has never heard about something like unsupervised learning. Is there somebody? So everyone in this audience knows what that is, right? Okay. Or I will simply explain. Unsupervised learning is a problem where we have data for which we do not have labels, and we would like to understand the data set better. And one of the ways how we can understand the data set is to be able to construct a way to create or recreate new samples from this data set. So if we have a very simple data set, like let's say the heights of men, right? We would say like average height of a man is maybe 170 centimeters, right? And there are not samples of people who are 5 meters tall, right? So in this case, an unsupervised learning would represent actually learning the probability density function of these variables. We are interested, or one way of specifying what is unsupervised learning is actually learning or maximizing the log likelihood on the data set that we have at our disposal. So we might want to formulate this problem as such, so that we have a function, or we have some kind of parameter class of models, and we would like to find the model which fits the data in the best manner. And why would we be interested in things like that? So let's say that we have more of a traditional problem like separating two classes. If we have the probability distribution function, or PDF for short, then we can exactly specify that if these two PDFs are overlapping, then we can tell or be sure how badly or correctly our model is predicting. So let's say that we would like to apply this for a more complicated task, such as image recognition. If we would have the PDF of all the images, then we would be able to specify with what false positive, false negative values or percentages we develop our algorithm. So we would be actually able to exactly specify or model our decisions, and that's very interesting. There is something that's called Manifold Hypothesis, which says that most of the realistic data that we deal with, such as images or sound, are actually located on something that's called manifold, which is a structure in a high-dimensional space that doesn't occupy the whole space, that most data is concentrated in certain regions. And this intuitively makes sense. For example, if we would take a picture of a cat and just modify a value of a single pixel, we as humans would still recognize it as a cat. But if we modify a large portion, let's say half of the image to white, so we just colorize the image, then we might occlude the cat. So it makes sense that the data is structured in some regions of the space. And if it is somehow structured, then we might want to be able to find this structure. And this is where this unsupervised learning comes in. I'll just stick with this. If we are able to create, for example, a function for which we put in a point in this space, of the input samples, and we have a function that tells us how far we are from the realistic samples. For example, we have an image, and we would like to know how far is this image to actually a realistic image of the class that we are looking for. For example, some animal. Then we can do things like modifying the image in the direction of the true representation of these images, so we can create better samples. So we can start with something random and actually converge to a realistic sample. And this is what unsupervised learning, what the research in this area tries to do. So there are multiple ways how to approach this problem. Some of them are laid out on this slide. So what I will be talking about is GANs, but there are also other techniques. There are techniques that are based on non-probabilistic models and probabilistic or generative models. And the reason why GANs are interesting or are so popular in research right now is because they have certain properties which are very likable. And that's because the methods in other classes are often not tractable, or we have to use some kinds of approximations to get the samples, or they have problems like it might take a long time to generate the sample. For example, in one of the tractable models would be a recent work from Google on speech synthesis, WaveNet, and the samples in WaveNet are dependent on each other in time. So at first, WaveNet generates a sample at a time, and this generation itself takes, each step takes a long time because it is generated by a neural network, and synthesizing 2 seconds of speech can take 2 minutes of computation. So it is not realistic yet to use this as an online speech synthesis on a cell phone, for example. GANs, on the other hand, have the advantage that they are highly parallelizable, and you can create samples really quick. And recently we have learned how to train them really well, and I will show you some examples of images that have been sampled from GANs, and the results are truly astonishing. I'll keep it until the end, so you'll see the progress on the way as I go through the various methods. So what does it mean to learn a probabilistic model? Let's say that we have some kind of class of models, a set of parameters that our model can have, and there is a true probabilistic model of the data. So the true data is the data that we have, for example, in images, how real images can look like. And we are moving in some kind of a set, and we try to model, we try to train our models in such a way that we get as close as possible to the true distributions. If we match the distribution, then basically we get to we might be able to recreate what I showed here, that we can we can arbitrarily set our threshold on the algorithms based on what kind of specificity or accuracy we want out of them. And if we have probabilistic distributions, we can measure the distance between these distributions. There's one metric that's called Backlight divergence, which basically says how different the distributions are, and it's defined as in discrete case as a sum of the probability of the model, in this case that we try to train, times log the same divided by the true distribution. And I'll show you a short demo of how the KL divergence can evolve. Okay. So in this example, I have two probability density functions. One is the ground truth in red, and the green one is the one that I am trying to fit. So the green would be my model. And as I move this model, I change its parameters. Nemal som na to sadať. As I change the parameters, I can see the evolution of the KL divergence. So as I get closer to the real distribution, the KL divergence goes lower. Here it gets to the lowest point, and as I get further away, the divergence increases. And as I go further and further, it can actually reach to infinite values. This can be done on this simple example where I have two normal distributions which are actually who have continuous probability density functions. And I'll just show another example where I might have a more complicated case. So now I have my ground truth is actually two Gaussians. So I just take a Gaussian mixture, and I have a model that doesn't have enough of capacity to model the real data. So as I move around, I actually get towards some kind of minimum, and but I cannot fully model the function because my model is not appropriate in this case. And this is actually something that we might see in the case when we are trying to recognize images or in some other real data, when we don't actually know how the true distribution looks like, and we just have some kind of we just test our models on the test sets and see which models perform better, but we actually don't know how appropriate actually the model is. So if we could compute the distance between the true distribution and our model, that would be a tremendous help, because then we could guide our algorithm towards the true distribution. Okay. Yeah. So this is an example which shows pretty much the same thing that I had on the animation. So this is where I get towards the GANs. In this, what we do in the training objective in GAN is that we have a generator function which creates samples and training set for which we do not need labels. And there is another function which acts as an adversary, which is basically a binary classifier that tries to tell if the sample comes from the from the training set or has been generated. And you can formalize this task as a minimax over this expression. I will just get into it. And the formulation is as follows. So we take a sample from the training set and minimize the expected error, and we also minimize the difference from the other side, so from the generator itself. And in the training algorithm, the generator and the adversary are training at the same time. So we start from an adversary that cannot really distinguish what is real and what is fake, and the generator slowly tries to approach the true distribution of the data based on the feedback from the adversary. So in the previous slide where I had the parameter space and the true distribution of the data and our model, we moved the parameter class towards the true distribution as the generator is learning how to generate more and more realistic data. Basically, this objective, it approaches a point, or the solution comes to the point where the adversary cannot distinguish the fake data from the real one, and at this point we have trained our generator to produce as high quality samples as it's possible. Of course, the problem can be that the adversary, the judge of these generated samples, is not the true data distribution itself, because we don't know what that is. If we knew that, we wouldn't be talking or trying to solve this problem in the first place, because we could just base our algorithms on the PDFs or sampling from the PDF. But it can guide the generator towards the true distribution of the data. And the training, there's a problematic phase of this training where the adversary actually produces data that are either all the time would say that they are true labels, while they are not. So the adversary is not very good at discriminating fake from real, because it doesn't model or approaches the true distribution well enough. And in this case, our generator cannot learn very well. And another issue is when these algorithms, while solving this training objective, we get to a point where where we reach a saddle point. So it is not clear in which direction the training or the gradient descent should go. This is the outline of the algorithm from the original paper from Ian Goodfellow in 2014, where he introduced this technique, and it is quite straightforward. So in the training iterations, we sample the real data from the generating distribution, and we sample noise samples from a noise prior. The generator has to generate the data based on some kind of input, and this input is a noise. So it is not deterministic. There is some kind of random noise, a random initialization, and it should produce a sample. We update the discriminator by using stochastic gradient descent on the training objective that I had in the previous slide. So the sum of the discrimination on the real and on the fake data. G in this case is the generator, which has the input, the noise sample. And in some variations, we might want to train the discriminator more times the generator, so it is in a way ahead of the generator, so it can produce more feedback to the generator, because at the beginning they both start at the same phase where the generator is not trained yet, so it doesn't know. The discriminator is not trained yet, so it doesn't. Its output, the discrimination doesn't really have some representational value. But as both of these are jointly trained, the discriminator and the generator learns how to process the output, and the discriminator the value. Yes. That is a good question, because of the training problem, that if we train the discriminator on all of the training data, it will always say that the generated samples are fake. So it doesn't, because the generator puts out some kind of output, and it always gets the feedback, it's fake, it's fake, it's fake. You don't know in which direction you have to go, in which direction the gradient descent has to go, because there is not enough of information. If you get information like these 9 samples you produced are fake, but this one is real, then you know that you have to update on the real one, and you get a direction in which you have to move. It's kind of like raising a child. Like if you tell the child, you shouldn't do this, you shouldn't do this, you shouldn't do this, and you don't show the supporting behavior, then it doesn't know in which direction its actions should go. So it's in this way, it's kind of similar. Does that make sense? Yes, exactly. Yes, exactly. Because we are moving in space of these generators that I'll be showing, that they generate up to 64 by 64 pixels and 3 colors, RGB. So it's a very big output output space. So if you do not have a direction in which you should move, then it's very difficult to actually generate a sample. And so this training procedure updates on these steps one by one, as I explained, and then we update the generator. So it's really it's been likened to a game where you have the criminals and the police, and they try to the police tries to find the criminals, the fakers, and the fakers are trying to become so good that they cannot be discovered. So that's kind of an analogy. And once we have these gradients, then we can use any standard gradient solver, such as RMS-prop or Adam solver, to guide the gradient descent. Yes. Yes.
The noise generated from the samples,
the noise is Gaussian noise or uniform noise. Yes. And demo. Yes. On the PG, sorry. The noise prior is just the Gaussian noise.
Okay, and then when you provide the updating, the data parameters, so these data are parameters of the Gaussian. Okay.
Yes. Okay, I'll show you a demo of this is actually that I have computed on my computer. Can you see? I don't know how to put this like full size, but I think it's visible enough. So at first, so this is a generator or GAN that has been trained on Místo, the standard handwritten digits dataset. And at first, the samples are the generator is not trained, so it outputs random noise. And as the training proceeds, you can see that there starts to appear some kind of images, and as the training goes further and further, they get crisper and more visible, and some of them might slightly change the shape. Or, for example, this one kind of looks like a 6 or an 8. It's not entirely clear what that should be. And I should note that the input in each of these is the same noise vector. So for the same noise, we generate these images, and the discriminator is judging whether it is a fake or realistic enough to the original digits. And we can see that the 6 kind of moved to a real 6, now it kind of turns to an 8, and but some of the other ones are clearly visible that they are the real images. And I have made quite a lot of samples, and but the algorithm converges. Or it is difficult actually to say when the algorithm converges, because we don't have something like test error or something like that, because this is probably the most difficult part about adversarial networks, is that it is difficult to judge on how realistic the output is. Because we can look at it as humans and say, oh, okay, this looks good, but we would like to actually have a good metric that gives us some error number or something like that that we can optimize. There is no actual clear answer on this yet. One of the things that have been used is some pseudo-metrics, such as if you generate images, you classify these images using some kind of standard classifier, such as Inception Net for image classification, and you report the score on these, and you can compare the generators between themselves, but it is not exactly the best way how to evaluate the error. So there people have used things like having actually people going through these samples and classifying, okay, this sample looks better than the other one, or having people as discriminators, where this was in the Pigs to Pigs paper, where they take the real and the fake data and they actually give it out to people if they can discriminate between the two. And some of the scores have been, depends on the problem type, but about 20 to 30%. So we have actually methods that can create samples that are about 20 to 30% realistic to people now. And this will get much better very shortly, probably. So this was the demo. And now I'll get more to the visual part after I have this theory. So one of the popular architectures that was very successful is DC-GAN architecture, which, this is the architecture of the generator. So as the input, as the random noise which is sampled from the Gaussian with 100 dimensions, and there are operations that are called deconvolutions, which are similar to convolutional filters in image classifiers, neural networks based on image classifiers. But it's basically the inverse operation, where instead of compressing the input, we decompress it as it becomes larger and larger, and we finally have an image of the size 64 by 64 and 3 color channels. And so this is again example on the MNIST. This is the results from Goodfellow GAN and from DC-GAN, and you can see that the digits are much crisper, and some of these you couldn't really tell if it's generated or not. Like these 8s, I couldn't tell the difference between the original data and the generated. And this architecture was used on data sets of bedrooms. So this is after one epoch of training the generator. It kind of starts to look bedroom-like, and this is after 5 epochs, which should be the same noise samples. And what is really interesting, this is trained on faces. What is really interesting is that as you as you take the noise sample and you generate an image, if you take latent representation in this generator and you take different samples, you can do actually something like arithmetics in latent space. So as here if I take the generated example for smiling woman minus neutral woman plus neutral man, I get a smiling man. And the same with glasses. So these generators actually learn a representation of the data in the latent space that is actually somewhat meaningful, that we can do this kind of arithmetic operations on them. And all of this is discovered basically by itself, right? So we didn't put any kind of supervised information. We just put a lot of faces, and what we get out of it is a representation on which we can do arithmetics, or we can do other interpolations. So if we get one face and we move in linearly in the latent space, we get actually a face rotation with its modification. So this kind of looks like a woman, right? And this is a man. So it turns from a woman to the man while it's rotating the face. So, we might see more work into investigating how these latent space actually what it represents once we learn once we learn how to generate the samples real well. There is a hidden structure to the models that we might be able to use, such as these, or maybe in some more sophisticated examples. This is generated album covers. From distance, it looks like some Pink Floyd's album cover or something like that. It's really impressive. One of the focuses in these image generations is on how can we upscale the size of these images. One of the works is a method called LabGAN, which basically starts with a very low resolution of the output image, and it takes this output, and along the noise vector that we put into the generator, we can also put another input. So these are what are called conditional GANs. The conditional because the generator is conditioned on another input. So we basically stage these inputs one after the other and generate more and more images with higher and higher resolution. There are certainly big problems with GANs, and that is when you train them, they are very unstable because the generator and the discriminator have to be trained jointly so that the discriminator doesn't become too good too fast, or it might not train fast enough. The thing is that we have to provide quality gradients to the generator. If the discriminator outputs only one type of the result, either all is fake or all are realistic images, then we don't get any information that we can provide to the generator, so it cannot learn very well. Another is what is called mode collapse, which I will explain in the next slide. And there are also qualitative problems, which I will show also examples of. And there have been a bunch of tricks that we can use for training GANs. There is actually a GitHub page where they are listed, so you can take an inspiration. Some of them are standard standard operations that you have to do with data when you are training neural networks, such as normalizing inputs or using batch normalization. Other ones might not be so obvious. Things like using spherical or Gaussian noise vectors instead of uniformly sampled noise vectors, or you should avoid sparse gradients, so neurons based on ReLU's rectified linear units activations are not very good because they can clip the gradient. So you might want to use actually activations like sparse ReLUs and so on. You should avoid max pooling because it has the same kind of training problem and so on. So there's many of these. You can see the page, and here are some samples. So the GANs have problems with counting. So here are some 3 heads or too many eyes, things like that. With perspective, it might be very twisted and so on. But we can see that, clearly see that these are some kind of weird animals. Like if you have taken some drugs, you might see something like this. So it certainly is based on something, but it's we can clearly see that these are fake samples, and they can have problems with global structure. And another thing that I have mentioned is mode collapse, which basically means that for many types of noise inputs, the generator outputs the same image. So if the target in this simple illustration is that we have the target are several classes that are clustered in this way, the generator might bounce around and fit one type of a cluster, but not all of them. So, for example, in the Manist demo that I had here previously, it would mean that the generator always outputs one type of digit. It doesn't output from all of the classes, for example. And this is interesting paper that I found that's called Wasserstein GAN. And this paper is very interesting because it actually makes sense of the loss function, where the loss correlates with the sample quality from the generator. So in the previous works, if you wanted to know how the generator, what is the quality of the images, you have to wait with the generator and look at the samples yourself and try to assess the quality of the generator, that maybe now it has trained well, and in other steps it has actually gotten away from some kind of better results because it bounces around the modes, such as here. And what this type of architecture is based on is that instead of the loss function defined as the one I had here previously on the slides, where the discriminator outputs only 0 or 1 for fake or real, you get the discriminator outputs distance from your fake data to the real samples. You could simplify it in this way. The metric is defined as this. I will not go very deeply into this, but this could be simplified as an analogy that when we have two probability distribution this metric is the amount of the cost of turning one distribution to another one based on the distance between the movement and on the amount of how much the distribution has to be changed. So it is there is an analogy that it's like moving a pile of dirt from one place to another. When we want one pile of dirt to look in one way, that's the data distribution, and we actually have our generator which looks in a different way, and we want to match the pile of dirt with the original distribution. So how much work it is to move one pile into the other one. And this is commonly used for comparing discrete distributions. For example, if we have histograms of two digital images, how far these histograms are one from the other. It is simpler in a discrete case than in continuous. And there's an example in the paper. I'll just very shortly draw actually what is on this slide. So if we have data with which lies in two dimensions, x1 and x2, and the original data lies on this interval, on this segment. It creates a manifold in the space of the samples, and we have a model. Let's assume that we have a model with appropriate capacity, and this model looks like this. It is also a segment, and it lies here. And if I would take a different perspective, this segment here is where probability density function of this distribution lies in. So for x1 and x2 lying here, this value is 1, okay? So if I, do you understand what I'm drawing here? Does it make sense? If not, raise your hand. So I just have a, yes? Okay. So, if I would take a 3D view, okay, of this, then I'll just do it in a different way. So I have PDF of x1 and x2, and this is equal to 1 for x1 equal to 0 and x2 in 0, 1 and 0 everywhere else. That makes sense, right? So this is my PDF for the true data. And I have a model which has appropriate capacity, and I move it around this line. And in case, I'm trying to find this manifold in this space. And if I would take a metric such as KL divergence that I had here previously, the problem with it is that it's infinite when I'm not on the line, and it's 0 when I'm exactly there. As I showed you the demo where I had the two Gaussians crossing over, that's exactly the same. As they move away, it gets infinite, so it doesn't really give me any kind of information. It gives me information when I'm close to it, but when I'm far, I'm lost. I cannot move. And there are other metrics such as Jensen-Shannon divergence, which has similar problems. And the authors in this paper claim that actually if we use this metric, then we get a meaningful result out of it, because then if the distance between my model and the true data is theta, then I get exactly how far I am from this true distribution, so I can move towards it. So I can use a simple gradient descent based on this value to move towards this result. And that's very interesting. However, if we want to use this, it has certain limitations that the metric is defined only under certain assumptions, and that is that the function that we try to the distance actually has to be differentiable, and it has to be, the value of the differential has to be bounded. So the changes in the discriminator cannot be too big. In other words, if the changes are too large out of certain bounds, then we cannot improve upon the generator very well. And so this is the algorithm, and the difference, I'll just go through it. The assumption, or I'll just add something. The assumption is that with this technique, we might not get the model exactly right on the first time, but because we know how far we are from the real distribution, we can slowly converge towards that, and we can use gradient descent as the solver to find the parameters of the model. So in this case, in this algorithm, we sample the real data. We again sample the noise input, and the discriminator and the generator functions that we had here previously are replaced by appropriate functions, which I believe I don't have here. It's in the paper, but basically these are the functions we have to guarantee that the output for each sample is within the bounds, and the authors do this by weight clipping the gradient. So we put basically a threshold on the results on how much we can move, so that we can guarantee that the difference is always within certain bounds. And this method works as long as we clip properly. If the clipping parameter is not set well, then this Wasserstein GAN doesn't have the guarantees that I have showed, which is main drawback of this method. But as long as we are within certain bounds, so, meaning that the generator and the discriminator have proper or have appropriate models, then we are safe. And we then based on the difference between these results, we do the gradient update with again standard techniques such as RMS prop. Are there questions to this? It might be a bit more difficult to understand. It's I definitely recommend the paper. It's very well written. It's a bit more heavy on math. There's proofs for these algorithms that there's proofs that if certain assumptions are true, such as the bound on the differential, then this actually converges and the loss corresponds to the quality of the generated samples. So I'll just cannot see it maybe that well on these images, but the bedrooms, as the loss goes lower, become more and more crisp in these examples, and there's also on their GitHub page you can see other examples like such as Místo and so on. Okay, now I get to stack again. Which is visually the most appealing of the GANs that I have seen so far. And this architecture is what it does is that as an input you get a text description and the output is generated image which corresponds to the text description. Now these models, the authors have trained them on a data set of birds and the description of the birds and on flowers. And the text description is embedded as word embeddings as an input into the stack GAN generator, and there are two stages to this. First stage, which produces a blurry, lower resolution image, and second stage, which upsamples the generated image up to 256 times 256 sample. The results are spectacular. The images look very photorealistic, and also the authors show, I'll just show examples now, so you can see maybe some of them might not exactly match the description. For example, in this case, the bird should have a yellow beak, but when it's turned with the tail, you cannot see the beak. So it's kind of doesn't correspond with the image description. But the output samples roughly really correspond to the descriptions, and the images are very crisp, very clear. And which is interesting is that these methods, or this method, doesn't have a strong mode collapse. So it means that for the same description, you get a different bird from a different angle, viewpoint, and you can do things. Yeah, this is an example on flowers. And these are nearest neighbors in the training set, and the generated image to these neighbors. So you can see that they are visually very distinct, and you can do similar operations, such as with the DC GAN that I have showed, that you can do linear interpolation in this latent space. So you can transform one bird into the other. So this red bird to blue bird, and you can in the middle see it's kind of blue reddish. And for some reason these ones are left turned and it turns into sideways. So also in this example. So maybe it's something with just the particular noise vector that was input into these. And there is a small mode collapse, such what I said earlier, that for the same input you get quite different images of the birds. There are also failures. mostly the failure cases are caused by bad first stage generation. So if the rough description is totally off, then the second stage cannot improve upon the details. And here are the failure cases for the flowers. And finally, I get to the model that I have shown you at the beginning of this lecture, which is pix-to-pix or image-to-image translation. And this is an attempt in solving a general problem of mapping one image into another image, such as these examples where we have a satellite image and we would like to automatically generate a map or day to night or edges to photos, the example I have showed you before, and labeling or automatic image segmentation. And these are problems which people have tried to solve as separate instances of problems. So there are people who work on image segmentation specifically, or there have been people which have tried specifically colorizing images and so on. And in this work, in the image-to-image translation, they use conditional GANs to solve all of these problems with the same technique, with the same method, and they show quite impressive results. Some of these are, some of the results of this paper are easier to spot that they have been generated, and some look very, very realistic. For example, the image colorization or labels to facades. The aerial to maps are easier to spot which are the fake samples, because the network outputs sometimes wobbly streets, or when there are highways, it's not sure that it's a highway and it kind of merges with a normal street, and there's instances like that which are very easy to spot for humans. But on data sets such as the labels to facades and so on, when they have tested, when they have tried to measure the error on these generated samples, it was the numbers I have mentioned, about 30% of the samples people have not realized they are fake images. And this is quite recent work. The first work that I have showed was in 2014, and in 3 years we have gotten to this. So it's quite incredible the pace of how these techniques and methods evolve. And for example, the Wasserstein-Gahn paper that I have showed you, it's a work that's 2 months old, and it has already been cited over 17 times, which is quite a big number for a scientific paper. That means in 2 months there have been 17 different people or different papers that have actually improved upon this. So it's quite incredible how fast the progress is. So these are the sources that I have used for this presentation. You can check them out. Most of the sources that I have used come from the 2016 NIPS workshop. I recommend checking it out. There's tons of materials available online which work out of the box almost. For example, the MNIST generation that I have showed you, you can download the source codes on GitHub, and it works basically out of the box, or you can find pre-trained models that the authors publish on their websites. So I definitely recommend checking this out. You can try to play on your own with these codes, and maybe you can improve upon them. That would be great if this lecture serves as an inspiration for you to look into this field. So from me, that's all, and thank you for your attention. And if you have questions, now it's a good time to ask.
We have like 5 minutes for the discussion. So if you have a question, please raise your hand, and I will pass you the mic.
Thanks. I actually have 2 questions.
Okay.
So first one, can you just quickly explain the conditional ones? What are you training on? And how is this different from just the generative case? And the second question is, can you explain the operations in the latent variable space? So the arithmetic and the transformations, what does it actually mean once I have a trained network?
Okay, maybe I can go back to this slide. Yeah, so here you can see in the stage 1, the inputs is the noise, which is sampled from the Gaussian, and the conditional input is actually the input from the text embeddings. So you have a random input and actual input as if you would train the neural network. You do 2 of these because you want to be able to sample different samples from the generator, and to be able to do that, you have to have some non-deterministic source, which is the noise. And the second question was
the operations in the latent variable space.
Yes. The operations. So if I can find the DC GAN. So as you have the noise vector, the operation, as you train the model, and you take the latent representation and one of the layers after the noise vector, and in case of images such as the phase rotation that I had here, or these operations, you take the latent representation and you just do linear interpolation. You take these values from the linear interpolation and you use them as the activations and pass it further to generate the sample. Does that make sense?
I'm not sure. So you have the weights of the trained network, and you move the weights in linearly, or?
You do not move the weights. Maybe I'll just draw it. So this is my input, the noise, and this is my output. This would be the whole image, right? And X would be the neural activations, the outputs of the neurons, which I take for one sample. So I'll say, let's have samples. So to get the latent representations, there is a transformation function f. So I would take f of z equals x. So let's say I take sample 1, I get x1, f of z2, I get x2, and the final result is y. So g of x1 is y1, g of x2 is y2. So this would be one phase, and this would be another phase. And here I just take x1 goes to x2, and I'll do the g of x in between. Okay.
One more question. Anybody?
Okay, so we have a discriminator network and a generator network. What if we change the inputs of the generator network? So that we shift a little bit the inputs of the generator network. What would be the result of that?
If we shift the noise,
Yes.
basically.
Just a little bit, just from.
But within the bounds.
Yeah.
Yes. Then for the sampling or for the training?
For the final output.
Okay, so you have a trained network. Yes. Then since you would obtain a different result, obviously, but it is there shouldn't be a principal difference between a random input and your specifically chosen one. So, for example, as I had the results from different training epochs, as I showed with the digits, those are trained with the same inputs, and so you can see the evolution of the generator, how it responds to different inputs. So if you choose a specific one or a random one, it doesn't really make a difference in sampling. If you want a sample, you can just take, okay, I just want some random numbers. There might be a difference maybe if the inputs are, for example, all zeros or something like that, because then in the network, I'm not sure how that would behave. If the value is specifically around zero, I think that might be problematic. But if it's a uniformly random value or Gaussian noise, then it's fine.
Okay, thanks once again to Michal for the presentation and for the discussion.